Cool. Yeah, so first of all, thank you to the organisers for inviting us today. As you'll notice, unlike the original lineup, I'm not Robert Pell. I'm about a foot smaller and much less well-spoken, but hopefully you'll still find what I've got to say today interesting. My name's Jordan. I'm the R&D manager at Miniviro. And today I'm going to be talking about life cycle assessment, which is an environmental quantification methodology we use in the raw materials sector. I'll describe what it is, what we do day to day, and I'll end up talking about how it links into a lot of the themes we've talked about today, particularly geomet and metallurgy in general. So we started our life 3 years ago. Just a bit of background about the company, first of all. We're a spin out from Camborne School of Mines, University of Exeter. And today we are a company of around 20 employees. This was actually taken this time last year, and we've doubled in size since then. It's been very rapid growth. And we've conducted around 120 successful projects within the raw materials and downstream technology space. Why do we exist? It's no sort of secret that environmental impacts are of maximum concern to the entire raw material space just now. Every year these diagrams are published, environment is always up at the top. And there's not really room for inaction anymore. Mining industry in particular has a really tenuous relationship with environmental impacts, and it just doesn't fly anymore. There's regulations coming in all aspects of the sectors, both in the upstream and downstream. And what we do day to day is that we help companies understand and work with the environmental impacts. Even ahead, before they've started extracting rocks from the ground, we can help them recognize what the impacts will be and help them plan to reduce it. So life cycle assessment is a globally recognized and robust environmental quantification technique. It follows ISO standards. And the sort of main thing about LCA is that it does capture CO2 environmental impacts, which is of course the topic on everyone's mind, but it actually contains a lot more impact categories. In the methodology that we use at Miniviro, we capture around 16 impact categories, which include things like acidification potential, water scarcity impact, particulate emissions, land use transformation. There's a whole lot of things that are included. But what the technique essentially does, in very simple terms, it looks at the raw materials and the energy you consume to make a product. This can be anything. It can be a shirt, it can be a lump of copper, it can be a computer. Anything you consume to make this thing gets included in life cycle assessment, in addition to any direct emissions that you make to the environment. And every LCA will have a main product, which we call the functional unit, and everything that is included in the model is normalized to this. Sounds easy, but of course, as with mineral deposits, all these really detailed deposit diagrams we've seen today, there's a lot of complexity within these ore bodies. There's complexities in what the metals are doing, how they behave, how they're processed, how you manufacture things. But as long as you think of it in these terms, everything else I say today should be pretty simple. Raw materials and energy in, and any emissions out the other side are taken into account within the system boundary to make your product. And normally what we do at Miniviro is we start at the very start. We call it cradle to gate life cycle assessment, which looks at the extraction of the raw materials to make your product all the way to the completion of your finished item. So once you've got your copper concentrate, your doré, your battery, and it's ready to get sold on to the people purchasing them, this is what we include within our system boundary. And anything that you consume within this to make your product is calculated. And then everything that is included has an environmental impact, and we sort of tally all of this up and work with the customers. But it doesn't really stop there. Within life cycle assessment, you can also extend to the end of life of that product, look at how it's used day to day and how it's disposed of or recycled. So really, life cycle assessment can be as focused or as wide as you want, which adds infinite complexity into the models, but it keeps it interesting. Something interesting within LCA as well, when we're talking about just the CO2 impact, life cycle assessment inherently includes all scopes of emissions. So Scope 1 and 2 are the most commonly discussed environmental impacts within the CO2 sort of landscape. That is the direct emissions that you emit by combusting fuels. Scope 2 are related to electricity that you purchase and consume. But Scope 3 are often left out of a lot of other ESG methodologies. Life cycle assessment captures this, any materials that you buy and consume to make your product, they've been made somewhere upstream. They've consumed electricity and fuel to make. So if you're producing a product that uses any of these materials, you're responsible for these impacts as well. You can't just buy acid and soda ash and different parts of metals to make your product and sort of get away with the impacts. The person using them is responsible, but life cycle assessment captures all of this, and we can help companies plan for ways that you can reduce it. So now the principles have been explained, I can talk about the work that we tend to do day to day. So we've worked very prominently in the raw materials sector, but this is mostly skewed towards the battery, lithium-ion battery sector. So materials that are being mined with the purpose of going into lithium-ion batteries. So we work mostly in the sort of decarbonization tech. One of our sort of most prominent sectors we've worked in is in lithium. It's the trendy mineral just now, loads of attention on the resource supply for this. And what we did a few years ago, we were one of the first companies to have public data on lithium hydroxide life cycle assessment. And what we did, we looked at a functional unit. So the exact same product, which was 1 kilo of battery grade lithium hydroxide monohydrate being produced from different places in the world. It's the exact same product at the end, but the route to get to there from extraction to purchasing for putting into batteries is completely different. So hopefully I can demonstrate just how variable environmental impacts can be for a single product. Here we took 3 examples. We took lithium hydroxide initially extracted from brines in Chile, lithium hydroxide produced from brines in Argentina, and a third situation, which was spodumene mining in Australia with chemical conversion in China. So you're arriving at the same product, but the journey is completely different. And if you think back to what I said at the start, the material and energy consumptions all down this chain will vary. And if you look at the life cycle impact results, so the functional unit is always, we're talking about CO2 here, but it's kilos of CO2 per kilo of your functional unit. It varies quite significantly depending on where you're sourcing materials, what you're doing in between. The difference between Chilean brine origin and Australian spodumene origin is actually 3 times higher. So a battery using however many kilos of this product in their manufacturing, if they're purchasing this one, their battery is going to entail that entire impact. And they can see, if you're thinking about different materials in a battery, each of them have this methodology applied to them. And if you aren't really being careful about sustainable sourcing of these materials, the impacts can kind of build up and build up and build up. So this is the sort of power of what we do day to day. We can help companies recognize this and look at ways they can source different materials, different energy consumptions in their chains, and really sort of make sure they're making as sustainable a product as possible. Another example, which is about even scarier, is with graphite. So one of the white papers we produce, by the way, if you can go on our website, we've got a lot of material on here that I'm going to talk about today there. With graphite, a commercial database had a baseline value for a kilo of anode grade graphite. The more work we did within the graphite space, we started to realize that our results were often 10 times higher than this. This was all verified throughout, and we realized that the commercial database value for LCA for graphite was using a limestone quarrying proxy. It had nothing to do with the materials and energy consumed to make these products. So a lot of people were using this value in their battery LCAs when it's actually 10 times higher for every kilo of graphite, which is about half of a battery. So again, you can start to see same functional unit, totally different impacts depending on where it's made, how it's been processed, loads of different things like that. And again, another very current one, nickel. Within batteries, we're moving towards more and more nickel-rich chemistries within the cathodes. And depending on where you're getting your nickel, yeah, you could entail 10 times higher impacts from some of these. I mean, HPAL is pretty popular these days, and there's a lot of companies purchasing nickel from here. Every kilo of this entails that embodied impact. So again, this is the sort of thing we do day to day. Really look at these systems, what has been consumed to make them, and then report this as an environmental impact and help people not do this. And if you combine this all together, you've got a battery model. This looks very similar to the model I presented at the start. It's just a system boundary, everything that's sort of included to make a lithium-ion battery, from the extraction of the materials and also including the manufacturing stage at this point. Again, material and energy is in and any direct emissions out. We've got a white paper on our website in which we kept the LCA model static. So everything about the model except these 5 green boxes, which are the 5 key cathode and anode materials. Within this, we looked into our database for LCA values for these materials and varied them a little just to see what the difference in impact would be for a final battery pack. and the impact pretty much doubled. This isn't thinking about anything to do with the electricity used to make the cell, aluminium, copper, any reagents. It's just those 5 materials, and it doubles the impact depending on where that you're going to source them from. So you can start to see how sensitive these models can be and how much impact one single material's sourcing can have on a final product. So yeah, this is the bread and butter of what we do day to day. And yeah, you can read a bit more about these white papers on our website, or ask me if you want more details. We also tend to do reports for clients within the space and help them recognize where their hotspots are, where are the sort of big impactors on the supply chain. We worked with Tesla last year. No surprise, nickel is really prominent. The surprising one was graphite. A lot of people graphite is going under the radar, and the environmental impacts of it are getting sort of hidden in this conversation about lithium-ion batteries and lithium scarcity, but people need to pay attention to graphite. That's all I'm saying. Don't forget about the impact of it, and there's ways to do it sustainably too. So how does this feed into everything talked about today? Hopefully you can sort of start to see the links about what I'm going to sort of introduce, but with all these resources, particularly the battery materials, the demand is just skyrocketing. Around here, you've got graphite, lithium, cobalt in the top 3, with their increase as a percentage of what it was in 2018. And it's just crazy. The amount of demand that we need for these materials is just going up and up and up. And if every one of these are being mined with the same sustainability sort of impact from LCA scores as the highest impactors, we're going to be in trouble. The efforts we're making to decarbonize will not be worth it, because we've just moved the impact somewhere else, and we don't want that. So the role of the mining industry here is that they're the first step in this chain when you're making these batteries, solar panels, all these things that we're trying to install to make the world a better place. Mines are the people that are starting off this chain, and if they can get off on a good footing and ensure that they're mining sustainably, they're kind of setting the rest of the chain up for success. I've kind of listed some things here that could impact a mine's impact: the energy they're using, the types of explosives they're doing, the efficiency of the removal. All of this feeds into the LCA model, and again, we're sort of creeping towards the geometallurgy stuff. If you're optimizing for removing your materials in the most effective way for kind of engineering terms, you can then just plug all this data into LCA, and you can see side by side, we're going to optimize for efficiency. What does this do to sustainability? Are we using too much energy here? Are we being efficient here? What is the best block to attack first to sort of make sure we're keeping within sustainable means? And it might be as simple as electrifying a fleet, but if your fleet is then using a coal-based grid, it's pointless. So there's a lot of nuance to what is going on. And the thing about LCA that we've recognized as a company as well, the earlier that you have these insights, the more power you have to change the direction of a project. If you get to this end and you've already dug out your metal and you're like, oh, we've just completely polluted everything round about us, oops, we'll put some grass over it and make it into an Eden project. Not the good way to go. If you're doing LCA, the earlier on, you're going to struggle for data, but the data you do have, you know what your deposit is, what the mineralogy is going to be. You have a rough idea of how you're going to get it out of the ground, a rough idea how you're going to process it. This can be used in LCA early on. Yes, the data quality will increase the more the project goes on, but you can start to have these insights and plan for it. You might be missing a huge hotspot in your production, and by doing LCA ahead of time, you recognize it, you can adapt your methodology and make sure that you're competitive, because at the end of the day, these environmental impacts are becoming regulation. European battery manufacturers need to know the source of the materials. If they're planning ahead, they can plan for this, and they can make sure they're sourcing their nickel, graphite, lithium from sustainable sources. And it feeds upstream to the miners. They're under pressure to make sure they're sustainable, so they can shout about being the most sustainable copper source, most sustainable lithium. Without greenwashing, they need to do it properly. I think it seems to stick halfway each time, doesn't it? Oh, yeah, okay. So we're here at geometallurgy. So hopefully all these things are coming together. We did a study with the GTK and a few researchers from University of Exeter, I think last year, where we united the principles of LCA and geometallurgy together. So within geometallurgy, you're looking at your ore deposit and thinking about what the optimum way to extract it is based on the chemistry, the geology, all the different aspects that everyone today spoke about. This can feed into LCA really nicely, and you can have your sustainability and your block model side by side. The paper, I think, is in, oh God, is it in Nature or something like that? There's links at the end, you can check it out. This really complicated diagram basically summarizes everything. It talks about how you can approach block models from an optimization point of view. It talks about how this feeds into your material and energy consumption. And then how this feeds into LCA, because if you're basing your block model and you're thinking about what the geology is, what the mineralogy is, what the chemistry is, and planning ahead for it, you can then start to attach the materials and resources you're going to use to get to your final product. And there's your LCA. You can plug it into the sort of LCA database that we develop at Miniviro, for example, and you can sort of have this sustainability in your head right from the start, so it's not a shock when you get to the end. And you can actually sort of then loop this back round to plug it back into block models. So you can optimize by efficiency, transfer this into an environmental impact, and then use this as a factor for which to view your ore deposit. And it might change how people mine things, because if a mine is under pressure to mine in the most efficient way in terms of sustainability, this may sort of blend quite nicely with the geometallurgy, or it hopefully will. And yeah, basically it's like a nice loop. You can have these simulations running side by side and optimized by both at the same time. I wasn't part of writing the paper, so I'm not sort of very clued up on how this matches, but if you've got any questions, I can forward them on to the authors. But essentially the bottom line is, if you're taking the time to optimize for your mining project based on properties within the geology, which are sort of, you're already going quite a lot of effort to unite geometallurgy, because we said you've got these silos with different pieces of information and everyone's trying to unite to go in together. I think adding sustainability on top of that isn't too much of a stretch if you've managed to unite the engineers and the geologists and everything like that. We've also worked with a mine planning company called MapTech, where we've actually automated this. So these guys do mine scheduling, they have block models, and they know exactly how much resources it's going to take out to get each block, and that easily transfers into LCA. So again, we've got a white paper on their website that you can view, and it talks about sort of seamless integration of life cycle impacts per block. So you can really get granular with this stuff. It can be the life cycle impact of a total mine, or you can do it by stage, day, block, whatever. Each thing, again, material and energy inputs, it's all contained within the information there. And just to round off, we'll talk about some work that we've been doing recently. We've actually developed a software that's been used within the space, Mine LCA, which allows people to conduct life cycle assessments by themselves. So we support and do a lot of consultancy work where we work with the clients, but a lot of people we work with tend to sort of prefer to work out themselves and iterate and work on their mine plan as they go and work out the sustainability and sort of do that process to really optimize and sort of build it into their sustainability plans. I've not got much time to talk about it, but if anyone would like to see the software in action, it is commercialized now. You can drop me an email and I can demo it for you one time. But basically, it distills the knowledge that we have built within the last 3 years, provides the data to you, and as long as you know what your output is, how much diesel you use, your electricity, your explosives, that's the minimum you need. And most people know that when they're planning for a mine, they know how they're going to get it out. It's very seamless to transition this into a life cycle impact using the software. And we've actually been trialing this with GSL recently, where we are looking at mineral processing rather than mining. So again, I keep going back to the same thing. You're still using materials and energy to make a product. It doesn't matter what that is. It doesn't matter where you draw the system boundary. And one of the most powerful things, if you think back to the lithium and graphite and nickel examples, you can arrive at the same product and try different mineral processing routes to get there. These are going to entail different materials and energy. And then by looking at it in a life cycle impact setting, you can start to see what the most sustainable way to do it is. So with GSL, we're looking at doré production from gold ore, 2 different processes in one. This is just hypothetical, but you could add in an extra step that might optimize the efficiency of your mineral processing. This can directly be translated to see if it's a sustainable option as well. So if you're maybe putting something in to, I don't know, enhance the way that the chemistry, the sort of geochemical processing works, this might add cost into your project, but it might actually save you some energy further down the line because you're not having to use as much physical processing. So we're basically working with them. We're hoping to have a white paper out pretty soon, so you can watch this space and hopefully there'll be some interesting insights for you. This is more on the metallurgical side, but the principles are the same, material and energy in, and you can see what the impact would be at the end. And everyone has a role to play within this. The engineers who are designing facilities can have sustainability in mind. People that are investing are having to make sustainable decisions. And the people that are manufacturing things using all these materials have to have sustainability in mind too. The EU regulations are coming in a few years for these battery manufacturers, and there's like no time for inaction now. So everyone has the ability to get behind sustainability now. The data they have existing is usually good enough to be plugged into a preliminary model so they can start understanding and increase their the granularity of their environmental impacts with time. And yeah, we've got loads of resources out there. If you check out our website, we've got our nature paper, we've got the geometallurgy paper, and some other reviews with commodity-specific LCAs. I think we've got lithium, graphite, and battery LCAs available. But if you've got any questions about anything I've talked about today, or I didn't go into enough detail about the geometallurgy, give me a shout or send me an email, and I'd be happy to talk to you about it more. Thank you very much. Any questions? Yes.
Jordon, where do you think we're at with the maturity of this, that the LCA score might start to directly impact on price penalties or price bonuses for the raw commodity?
Not sure what the recent like regulatory side of the raw materials side is, but I know for batteries, the regulations that are going in for people producing those, there's a recycled content quota that they have to hit, or they're not going to be able to sell their product. Manufacturers in Europe that are purchasing materials, even if it's from China or Australia or America, have to have LCAs done. They have to have the knowledge of where their materials are coming from. I don't know if that will translate to price penalties, but they will not get investment or permissions if they're not demonstrating that they know ahead of time what their impacts are. I think what I know British Volt was a sort of different situation that's quite topical just now. There's so many complexities in setting up these projects, and it's not just like, oh, we're going to make batteries and it's going to save X amount of CO2. There's a lot that's going into it to make sure it's not just another sort of trendy fad that people are just jumping on the bandwagon to make batteries. The EU are really pushing these regulations forward to make sure that it can't be done unsustainably, but the regulations are pretty strict. Like that, people are having to understand everything from the entire source of their nickel sulfate down to how they're going to prove what grid mix they're going to use within their mix. Because if they're using a portion of coal, that's going to translate into the LCA. They're having to demonstrate all of this ahead of time, and I know it's hard for the manufacturers, but I think it kind of has to happen. I do think that commodity sectors will be under something similar in the future. I don't know, this is just what I'm thinking, but especially things like lithium, where there's so much attention, I don't think it's far before there's environmental, like quite binding regulations further upstream too.
Hi, Jordon. Very interesting talk. Thanks. It might be a slightly unfair question for you, given your background, but I'll ask it and you may know.
Okay.
You were talking earlier on in your talk about the amount of CO2 that was produced from graphite deposits. It seemed extraordinarily high.
Yes.
Did you compare graphite deposits from around the world, or were you just looking in one particular place? And you found exactly the same for all of them, did you?
So the figures that are up there were Chinese graphite, so produced predominantly, I think is the Jiangsu region is where most graphite is produced, and then in Mongolia, purely because of the electricity demand to make anode grade graphite mixed with quite a fossil fuel rich grid mix. That's why they're so high. And this is the dominant source of graphite just now. You can transplant that exact same process to make the same product into Norway and use hydropower, and it would be significantly lower because the main driver behind graphite impact is electricity. But I know that China are very quickly decarbonizing like their efforts within that. So Europe needs to quickly get the competitive edge by demonstrating European graphite, because I think as soon as China sort of uses a less impactful grid mix, they'll be reducing their impacts as well. But for current production routes and the popular routes that people are buying graphite for lithium-ion batteries, that's the sort of standard now for natural and synthetic.
Thanks.